Let's see if we can understand how proofs work. Okay, so what kind of thing do we intend to prove with a proof? Well, we're going to prove theorems. So what is a theorem? Well, a theorem is a kind of claim. It must have premises. There must be some starting point, even if it's implicit, and a conclusion. There must be some point to the claim. So a theorem is the claim that the truth of the premises guarantees the truth of the conclusion. In symbols, the premises imply the conclusion. A proof of the theorem is a careful argument that this claim is true. Because a theorem is an implication or a guarantee, the only way that it can fail to be true is that there's a situation in which all the premises are true, but the conclusion is false. A proof must show that this cannot happen. In most situations with true premises, the conclusion might also be true, but even one situation with all true premises in which the conclusion is false ruins the guarantee and disproves the theorem. So how do you construct a proof? Well, usually proofs are constructed according to common patterns. What is meant by a pattern? Well, in this context, a proof pattern is a strategy or move you can make in the proof construction game. The best way to understand these moves is to see them in action. We will prove the following simple theorem. The sum of two even integers is even. 2 plus 2 is 4, 2 plus 4 is 6. Statements like that. What are the premises? That is, what is the starting point, or what is assumed to be already known? This points us to our first move or pattern. Pattern 0, identify what is already known. The word integer signals that the properties and arithmetic of the integers, and even simple algebra, is a given. We need to recall these properties as necessary. See the appendix numbers in the text. Part 2 of pattern 0, the adjective even identifies a concept which has a precise definition. We need to know that precise definition, and here it is. An integer n is even if there's an integer q such that n equals 2 times q. That is, 2 must be a factor of n for n to be even. A definition is a two-way street. If we know that n is even, then we know that there is an integer q such that n equals 2 times q. On the other hand, if we know that there is an integer q with n equals 2 times q, then we know that n is even. Let's summarize what we have learned in a chart that records what we assume and what we must show. So here's our starting point. We can assume the integer properties, the definition of even, and we must show that the sum of even numbers is even. Okay, our next pattern, the concluding part of pattern 0, is we can assign names to relevant entities. So the sum of two even integers mentions a sum, mentions two integers. Let's give names to these important entities. So we'll call one of the integers m, the other one n, and the sum we'll call s, so that s equals m plus n. Therefore, the premises are, aside from the integer properties and the definition of evenness, that m and n are even, and we've defined that s equals m plus n, and the conclusion is that s is even. Using this information, here's the situation now. It's a little bit more concrete. We assume the integer properties are true. We assume the definition of even. We've added the definition of s equals m plus n. And we have to show that if m and n are even, then s is even. Okay, we have to prove a guarantee. That's an implication, an if-then statement. To prove a guarantee, P implies Q, we can assume P and show Q. That is, we can assume that P is true and show that Q is true. The reason that proves the guarantee is that the only way the guarantee can fail to be true is if P is true and Q is false. So we're going to show essentially that can't happen. Since our theorem's claim is m is even and n is even implies s is even, we're going to suppose that for the sake of proof, that the condition of this conditional is true. That is, we're going to assume that integers properties, the definition of even, the S equals M plus N, and we're going to assume that M is and N are even, and we only have to show that S is even. So in doing this, we have more things to assume and less to prove. Pattern 2 involves disassembling conjunctions in this proof. If we know that M is even and N is even, then we know two things. We know that M is even, and secondly, we know that N is even. If we include this in our diagram, it becomes a little more flexible. We know that S equals M plus M is even, N is even, and S is even. Pattern 3, we replace concepts with their definitions. Because M is even, we know that there's a J, an integer J, such that M equals 2 times J. And because N is even, we know that there's a K such that N equals 2 times K. We have to show that there's an L such that S equals 2L in order to show that S is even. Making this explicit makes our task concrete. We've imported the definition of evenness into the explicit definitions. So we have the integer properties, we have the definition S equals M plus N, and we know about J and K, and about that we need to show that there exists an L such that S equals 2 times L. Well, if you look at these, well, we want to show a connection between S and the number 2. And you can see in our assumed properties, we know that S equals M plus N, and we have definitions or expressions for M and N that involve 2's. All these moves are designed to lead us to the core insight we need, the nuts and bolts of what makes this theorem true. This situation both requires insight, in this case it's not extreme insight to see how to proceed, but also provides insight into why the theorem is true. So S equals M plus M, that's our definition of S. Then because M and 2J name the same number, we can replace M with 2J, and because N is equal to 2K, we can replace M with 2K. And then because we know the integer properties hold, we can factor out the 2 using the distributive property of multiplication over addition to get that S equals 2 times J plus K. So if we choose L equals J plus K, then we find that S equals 2 times L. So we've found an L that demonstrates that S is even. So far, we've been diving deeper and deeper towards the into the nuts and bolts of the proof, and now it's time to try to come back to the surface. Here we use the definition of even the other way around. If we have found an L such that S equals 2 times L, then we know that S is even and we were done. Well, we have found such an L. L equals J plus K. So we know that S equals 2L. And then, so we know that S is even, given the assumptions, and we're done. It remains to write up this proof in good Mathlish. Like a scalpel, a proof is sharp and goes straight to the core insight. Reading a mathematician's proof is like watching a surgeon wield a scalpel. It's not for the faint of heart. Okay, here's the write-up. Here's a version of the proof in Mathlish. Proof. Okay, every proof begins with the word proof. It's like a style or a convention, and every proof ends with a little mark at the end, like the black box here in the lower right. And those two marks cordon off the words in between and say, this, what's in between is supposed to be Mathlish, okay? Suppose M and N are even. Then there exists an integer J such that M equals 2J, and there exists an integer K such that N equals 2K. Then the sum, S equals M plus N equals 2J plus 2K, which equals 2 times J plus K. Therefore, there exists an integer L, namely L equals J plus K, such that S equals 2L. This means that S is even. So the proof is fairly condensed. It doesn't mention things that are already known, doesn't mention definitions. It goes straight to the core insight, the ideas and calculation that demonstrates that it's true. Here's the proof laid out claim by claim. Now, each sentence here, each claim corresponds to one of the patterns we mentioned. For example, suppose m and n are even. Well, we've chosen names m and n, but when you suppose that m and n are even, that's because we are behind the scenes realizing that we are proving a guarantee, an implication, and we're supposing the condition of that guarantee is true in order to show that the conclusion in step 6 is true. So the guarantee, the proof from concluding 1 and 6 is that first pattern about how to prove a guarantee. Items 2 and 3 are both related to, they both embody replacing a concept, evenness, with the definition. 4 and 5 relate to the core insight. 4 relies on integer properties in that insight, and 5 is the identification of L and its use to show that S is even. Going from 5 to 6 is using the definition of evenness the other way around. What you'll be asked to do in this course with respect to proofs is largely be given a proof like this as a list and try to be able to recognize what some of these patterns are as they're being used. Now, an actual mathematician would likely just deploy some version of the universal elitist proof, trivial, end of proof, or perhaps proof, obvious, end of proof. What they mean by this is each sort of realm in which you prove something has to start somewhere. An actual mathematician is starting at such a high level that these things are part of what they already know and they can see what's going on. So there's no need to give explicit proofs except as exercises for students. Well, that's it for now.